In the vast and mysterious expanse of the universe, we've only scratched the surface of what lies beyond our own solar system. As we look towards the infinite beyond, we're met with the tantalizing possibility of other worlds, other planets, and perhaps even other life forms. Among these celestial wonders are the exoplanets, planets that orbit stars other than our own sun. In this documentary, we'll embark on a journey through the cosmos to explore some of the most intriguing exoplanets discovered to date, including the enigmatic Proxima b and the captivating TRAPPIST-1 system. But our exploration doesn't end there as we delve deeper into the mysteries of the universe and discover countless other exoplanets that may hold the secrets to our understanding of the cosmos and the origins of life itself. So join us on this journey of discovery as we venture beyond the familiar and explore the unknown wonders of the exoplanet universe. Think for just a moment. Every time you look up into the night sky, just 4.2 light years away, a mysterious world awaits our discovery. In a star system near us, is there a mysterious exoplanet that may hold the answers to some of our deepest questions about life beyond Earth? Welcome to the mysterious world of Proxima b. But what makes this cosmic neighbor so attractive? Can Proxima b really harbor the conditions necessary for life? Or is it a barren, inhospitable wasteland? How do its unique characteristics challenge our understanding of planet formation and habitability? In this fascinating journey, we'll delve into the heart of the mystery of Proxima b, exploring the complexities of its celestial dance with its parent star, its elusive atmosphere, and the tempting prospects of finding another Earth right at the back of our cosmic space. As we move beyond the familiar constellations of our night sky, we reach our closest cosmic neighbor, the Alpha Centauri system. Located just 4.37 light-years from Earth, this intriguing star system holds 3 separate stars in its gravitational embrace: Alpha Centauri A, Alpha Centauri b, and Proxima Centauri. Alpha Centauri A, the largest and brightest of the trio, is very similar to our Sun. It's about 10% larger and 50% brighter than our home star. Its sister, Alpha Centauri b, is slightly smaller and a cooler star, with about 90% of the Sun's mass and half its luminosity. Together, these two stars form a binary system orbiting a common center of mass with a period of about 80 years. Meanwhile, Proxima Centauri, which is the smallest of the brood or the run of the litter, is a small, dim, red dwarf star. Proxima Centauri revolves around the binary pair at a considerable distance, and it takes more than 500,000 years to complete one revolution. Although it is the closest star to our solar system, it is incredibly difficult to detect with the naked eye because of its faint magnitude. Magnitude is a measure of the brightness of a celestial object, with lower magnitudes corresponding to brighter objects. Alpha Centauri A, with an apparent magnitude of negative 0.01, is the third brightest star in the night sky, behind only Sirius and Canopus. This bright star is clearly visible to the naked eye, even from moderately bright locations. Alpha Centauri b, on the other hand, is somewhat fainter, with an apparent magnitude of 1.33. Together, these two stars form a single luminous point in the sky, and their total magnitude is negative 0.27. Proxima Centauri, however, is a very different story. Proxima Centauri, despite being the closest star to our solar system, is much less bright than its twin counterparts. This is primarily due to its red dwarf status, which means it emits most of its energy in the infrared spectrum. With an apparent magnitude of 11.05, it's too dim to be seen by the naked eye. This goes a long way toward explaining the problems astronomers have encountered in trying to study this elusive celestial neighbor. So the gravitational dance of these three stars has created a complex and dynamic environment that offers astronomers a treasure trove of information. As we continue to study the Alpha Centauri system, we not only learn about the complex interplay between its celestial inhabitants, but also uncover the secrets of the planets that call this stellar region their home. As we continue our journey through the Alpha Centauri system, we turn our attention to Proxima b, a mysterious exoplanet located in the habitable zone of its parent star, Proxima Centauri. Exoplanets, or extrasolar planets, are celestial bodies that orbit a star outside our solar system. The habitable zone, also sometimes called the Goldilocks zone, is the area around the star where conditions are neither too hot nor too cold. They're ideal for the existence of liquid water, the key ingredient of life as we know it. The size and location of the habitable zone depends on the size and temperature of the star. However, it is important to note that simply being in a habitable zone does not guarantee the presence of life or even the necessary condition for it to develop. Factors such as a planet's atmosphere, geology, and magnetic field play an equally crucial role in determining habitability. Although Proxima b has attracted considerable scientific attention, it's not the only exoplanet orbiting Proxima Centauri. In recent years, two other planetary candidates orbiting Proxima Centauri have been identified: Proxima Centauri c and Proxima Centauri d. The discovery of Proxima Centauri c was a testament to the ingenuity and persistence of astronomers. Most exoplanets are detected using the transit method, which involves measuring the drop in a star's luminosity caused by a planet moving in front of the star. However, this method only works when the planets are aligned with our observing position. Instead, astronomers have turned to the radial velocity method to study the Proxima Centauri system. The team behind the discovery, led by astronomer Fritz Benedict of McDonnell Observatory, combined data from the Hubble 3 precision guidance sensor and the SPHERE instrument on the VLT, Very Large Telescope, to determine the existence of Proxima Centauri c. This planet has an orbital period of 1,900 days and is about 7 times more massive than Earth. However, in various dimensions of Proxima Centauri c, in a 2020 article in Natural Astronomy, Paul Wood stated that the candidate's motion does not match the current best measurement of the host star's astrometric motion. Woods also suggested that Proxima Centauri c might be 5 times the size of Jupiter, which is much larger than previously thought. He speculated that the planet may be surrounded by dust clouds or a system of expanding rings, very similar to the Saturn system. When it comes to habitability, Proxima Centauri c is probably too cold to support life as we know it. Proxima Centauri b, on the other hand, is close to Earth in mass and is in the habitable zone of its star. However, the question of habitability around red dwarfs like Proxima Centauri remains a matter of debate. Red dwarfs can exhibit powerful outbursts, potentially destroying their planet's atmospheres with intense radiation. It's not known whether life can survive in such conditions. The discovery of another exoplanet, Proxima Centauri d, further expands our knowledge of the Alpha Centauri system. Proxima d, orbiting closer to its parent star at 0.029 AU, less than 1/10 the distance of Mercury from the Sun, has a mass of 0.26 Earth mass and an orbital period of 5.12 days. This makes it the lightest exoplanet ever measured using radial velocity methods. Although it's located outside the habitable zone, the discovery of Proxima d highlights the potential for many diverse worlds within our nearest stellar neighbor. As we delve deeper into Proxima B's unique characteristics, one of its most striking features is its day and night change. Because of its close proximity to its parent star, Proxima Centauri, the exoplanet, is probably in a state of tidal lock. That means that one side of the planet is always facing the star, resulting in perpetual daylight, which the opposite side is shrouded in perpetual darkness. This unusual cycle of day and night has a significant impact on the atmosphere and climate of Proxima b. Constant exposure to starlight on the day side can lead to intense heating, which can lead to the formation of a thick and dense atmosphere. Conversely, perpetual nights on the other side of the planet can lead to low temperatures, which can lead to a thin atmosphere, or even a surface covered with ice. The sharp contrast between the two hemispheres can create intense atmospheric circulation, with winds transferring heat from the day side to the night side, trying to equalize temperatures across the planet. The composition and dynamics of Proxima b's atmosphere are important detriments of its habitability. A dense atmosphere on the day side can help retain heat and maintain presence of liquid water, as well as provide protection from the intense radiation and starburst emitted by Proxima Centauri. However, if the atmosphere is too dense, it can lead to a rampant greenhouse effect similar to that on Venus. That makes the planet inhospitable to life. On the other hand, the rarefied atmosphere on the night side may struggle to retain enough heat to sustain liquid water, resulting in a frozen wasteland. However, the boundary between the day and night sides, known as the terminator zone, may offer a more temperate environment, where temperatures are stable enough to support the existence of liquid water and perhaps even life. Nevertheless, whether a planet is tidally locked or orbiting on its axis, there are several possible scenarios for what the atmosphere might look like. These depend on various factors, such as how the planet was formed, its distance from its star, and the types of gases present. Scenario 1. Dry, oxygen-rich atmosphere. In this first scenario, the water on Proxima b could have condensed a long time ago and most of the hydrogen would have escaped into space. This would leave us with an atmosphere that consists mostly of oxygen and/or carbon dioxide. This could happen if the planet formed close to its star, which would cause water to evaporate more easily. If this is the case, then the planet could be quite dry without much water on the surface. But on the other hand, if there's a magnetic field around Proxima b, we could see some really stunning auroras. Scenario 2. Wet, pristine atmosphere. The second scenario is quite different. Here, Proxima b could have retained its original hydrogen atmosphere or formed further away from its star. That would mean that it did not lose as much water over time. In that situation, there could still be a decent amount of water on the planet's surface. The atmosphere may still contain oxygen and carbon dioxide. Nevertheless, with a hydrogen-rich atmosphere, conditions for life as we understand it would be less favorable, since a hydrogen atmosphere does not support the same chemical processes that a carbon-based life on Earth relies on. Scientists have used climate models like the ones we use for Earth to figure out what the atmosphere and climate on Proxima b might be like. Depending on factors such as the presence of tides on the planet, the amount of water and carbon dioxide, etc., we can see many scenarios. For example, the planet may be partially or completely covered in ice, or there may be large or small oceans. It could be completely dry land, or a combination of all of the above. Even if Proxima b has no atmosphere, there is a possibility that it has water. One interesting idea is that water could be replenished by asteroids, similar to the recent finding on the Moon, which has the appearance of water encased in glass balls. To give you some context, researchers have discovered that there are these tiny glass globules present on the Moon, formed over billions of years. They were created when soil ejected during an asteroid impact cooled and fell back on the lunar surface. When China's Chang'e 5 probe discovered lunar samples in March of this year. Scientists discovered that these glass globules contained significant amounts of water. We already knew that there was water on the moon, but the origin and behavior of this lunar water is still unclear. It turns out that these glass beads may be a hidden reservoir of water. They release water into the dried soil surface on a cool and dark lunar night, making them a very important part of the lunar water cycle. Perhaps something similar is happening on Proxima b. If an exoplanet has been bombarded by asteroids over time, these impacts may have created large water reserves not subject to weathering by solar radiation. Of course, this is just a hypothesis. We still have a lot to learn about this planet. As discussed earlier, Proxima b is in the habitable zone, but much closer to its star than Earth is to the Sun. This close proximity means that Proxima b is subject to the strong gravitational forces of its star, Proxima Centauri, resulting in tidal forces acting on the planet. While the tidal lock stabilizes the planet's rotation, tidal forces continue to act on the planet. Tidal forces arise because of the difference in gravitational pull on the near and far sides of the planet, which leads to deformation and heating of the planet's interior, which can subsequently cause significant tectonic activity and volcanic eruptions. So how might these processes affect the cold night side of the planet? First, let us consider the potential benefits of tectonic activity and volcanic eruptions for habitability of the night side of Proxima b. Tectonic activity can help redistribute the heat generated by the planet's interior, potentially preventing extreme negative temperature on the dark side of Proxima b. In addition, volcanic eruptions can release substances like carbon dioxide, water vapor, and sulfur dioxide, which could help form a greenhouse effect to help retain heat on the night side. This can create a more temperate environment, such as one suitable for living organisms. In addition, tectonic activity can create underwater hydrothermal vents, which can be a source of heat and nutrients for life to exist on the cold night side. These hydrothermal vents could support chemosynthetic organisms that rely on chemical reactions rather than sunlight for their energy needs, similar to those at the bottom of Earth's oceans. However, there's also potential drawbacks to tectonic activity and volcanic eruptions on the night side of the planet. Intense volcanic activity can release large amounts of gas and particulate matter into the atmosphere, which could lead to a rampant greenhouse effect, making the night side too hot for life, or cause global cooling due to the reflection of sunlight back into space. In addition, frequent earthquakes and volcanic eruptions can be a serious problem for any life form trying to adapt to an unstable environment. The potential for the existence of life in such an extreme environment presents an exciting challenge for astrobiology. Let's not forget that telescopes play a crucial role in the study of Proxima b, which has generated considerable interest in the scientific community since the discovery in 2016. To date, several telescopes have been used to study Proxima b. The James Webb Space Telescope, or JWST, is one of the most prominent telescopes that helps us better understand the exoplanet. With its advanced infrared capabilities, JWST allows researchers to study Proxima b's atmosphere by analyzing the light that passes through it as the planet passes through its star. This information can help scientists determine the composition of the atmosphere and assess its ability to support life. In addition to JWST, future telescopes such as Louvois and Habex are expected to make significant contributions to our knowledge of Proxima b. Both are part of the 4 major mission concepts being considered by NASA in the 2020 Decadal Survey. The Habitable Exoplanet Observatory, or HABEX, is a next-generation telescope aimed directly at studying exoplanets, including Proxima b. With its star-shading technology, HABEX will be able to block the light from Proxima Centauri, allowing direct images of Proxima b without the bright light of the parent star. This would allow researchers to study the planet's surface features, atmosphere, and potential signs of life in more detail than ever before. The Large UV Optical IR Surveyor, or LUVOIR, an ambitious space telescope concept, is also designed to directly image exoplanets. It boasts a large segmented mirror with unprecedented sensitivity, making it ideal for direct imaging of exoplanets. LUVOIR's main goal is to photograph hundreds of exoplanets, including Proxima b, providing more information about the exoplanet's surface and habitability. In addition to LUVOIR and HABEX, other telescopes like LYNX and ORIGINS can provide valuable information about Proxima b. The LYNX X-ray Observatory can provide insight into the high-energy processes occurring in the Proxima Centauri system, while ORIGINS, a far-infrared telescope, can study dust and gas in the system, shedding light on exoplanet formation and evolution. A mission to discover potentially habitable planets around Alpha Centauri has also been announced. The project, called Ptolemy, led by Professor Peter Tuthill of the University of Sydney, is a collaboration between the university, Breakthrough Initiatives in California, Sabre Astronautics in Australia, and NASA's Jet Propulsion Laboratory. Ptolemy's innovative design uses a custom-built space telescope with a diffractive pupil lens that scatters starlight in a complex floral pattern, making it easier to detect planets in orbit. The mission will focus on finding and analyzing the atmosphere, surface chemistry, and potential biospheric signals of nearby planets. Sabre Astronautics, which received $788,000 from the Australian government, will provide support for mission operations, including satellite communications, space traffic control, and data download services. The telescope's planned launch is no later than 2024. In conclusion, the study of Proxima b and other exoplanets will advance significantly with the development of the next generation of telescopes. These observations may ultimately help answer one of humanity's most profound questions. Are we alone in the universe? Life is a very rare phenomenon in our universe. For it to emerge and develop, there must be many factors: perfect temperature, water, important chemical elements, and atmosphere. Life on Earth is here because of the combination of all these factors, but it can't exist forever on one planet. Astronomical scientists right now are continuing to look for and study distant exoplanets, which can not only tell us more about the mysteries of the universe, but could also possibly become our home in the future. Today we'll tell you about the exoplanets most similar to Earth and whether they could be suitable for our life. The first planet on the list is K2-18b. It's a mysterious planet, 8 times the size of Earth and located 124 light-years away. K2-18b orbits the red dwarf K2-18, which is about 1.5 times cooler than the Sun. The planet is very close to its star, the distance between its orbit and the star being about 13 million miles or 2,100 kilometers. So 1 year on it takes only 33 days. Despite this, its average surface temperature is 17 degrees Fahrenheit, which is slightly warmer than on Earth. In addition, because of this proximity to the star, the planet's probably experiencing wave blocking, so only one side of it is facing the star. However, according to scientists, K2-18b is in the habitable zone, meaning the temperature there should probably be balanced, which could mean there could be water on the planet. Almost 80% of dwarf stars have planets in the habitable zone. Perhaps scientists should focus on the study of such planetary systems to have a better understanding of the mechanisms of their development, therefore to establish how life is possible on such planets. Moreover, thanks to the enormous brightness of the star, Astronomers have been able to detect the planet and even give it a very complete description despite the considerable distance. Usually red dwarfs are dim and very difficult to detect, but K12-18 could probably be quite active. However, this in turn may hint at very strong irradiation of the planet's surface. Nevertheless, the planet's enormous size worries scientists somewhat. Since researchers know the mass and size of the planet, they can establish its density. The established density of the exoplanet is intermediate between the density of Earth and Neptune. Therefore, at this point, it's impossible to say for sure whether the planet is a super-Earth, a mini-Neptune, or even a fully aqueous world. The rocky planet scenario seems more likely because of Earth's more characteristic atmosphere, but the minor helium envelope with the considerable mass of the planet's core makes it look like Neptune or Uranus. Still, many scientists view K2-18b as a rocky super-Earth, so we'll do the same. Now let's look at the atmosphere of an exoplanet. In 2019, a team of researchers at the University College London found water vapor in the atmosphere of an exoplanet. Therefore, if K2-18b is still more like Earth, there might be water. In addition, the water vapor molecule may indicate the presence of hydrogen and helium. Moreover, scientists believe that the layers of an exoplanet's atmosphere may even contain methane and nitrogen, important for the emergence of life. Also, due to the probable presence of water vapor, the planet may form clouds, which also hints at the high metallicity of the atmosphere, and among other things speaks in favor of the habitability of many Neptunians. And yes, if the planet is fixed in a wavelock, then the clouds can only appear at the terminator, the dividing line between the hot and cold sides. On the other hand, a group of researchers led by Marcus Schuschere suggests that K2-18b has only a hydrogen-helium atmosphere and may not contain water at all, so it can hardly even be an ice planet. Still, despite many contradictions, K2-18b could be habitable. The planet's temperature and pressure, provided it has a solid surface and a metallic core, could probably be favorable for the development of life, albeit presumably extreme. Nevertheless, the planet requires a more detailed study to assess the potential for the emergence of Earth-like life there, more precisely. The next massive planet, LHS 1140b, already has a confirmed solid surface. LHS 1140b is 40 light-years away from Earth. The exoplanet is 7 times larger than Earth and also orbits a very small red dwarf about 10 times smaller than the Sun. In addition to LHS 1140b, there is another rocky planet in the planetary system, LHS 1140c, slightly larger than Venus. LHS 1140c orbits at a distance of only 2.5 million miles or 4 million kilometers, and therefore is not in the habitable zone like LHS 1140b. The exoplanet also has a fairly short orbital period. It only takes 25 days to make a complete revolution around the star. Nevertheless, despite its proximity to the star, the planet receives half as much light as Earth does from the Sun. Moreover, it's also likely to be tidally blocked, so only one side is fully heated. The temperature on the illuminated side of the exoplanet is -36 degrees Fahrenheit. In addition, perhaps the proximity to the dwarf could indicate strong irradiation of the planet. Oddly enough, the star's UV radiation is at an extremely low level. Therefore, the UV fluxes probably cannot do much harm to possible life there. Despite the low temperature, this probably does not prevent the existence of a probable internal ocean on the planet. The weak radiation from the star is unlikely to cause a loss of water from the surface and atmosphere on LHS 1140b. Moreover, according to a study led by Jason Dittman, the planet may have had magma oceans at some point in its evolution that could have replenished it with water. Another group of scientists believe that LHS 1140b and LHS 1140c may have formed outside the system, beyond the snow line, where they accumulated large amounts of water before migrating to their current orbits. Thus, the presence of water on this planet may be very likely. The exact composition of the atmosphere of LHS 1140b is unknown. A group of scientists led by a team of researchers believe it may contain water vapor and a small amount of hydrogen. However, another study suggests that the exoplanet's atmosphere may have a thin layer rich in hydrogen. So there could be ammonia, which fertilizes the Earth by increasing the oxygen content of the atmosphere, and methane. Nevertheless, in such atmospheres, oxygen and ozone molecules are actively destroyed. Still, several more transit observations are needed to accurately determine the composition. LHS 1140b currently meets many criteria for a favorable development of life, so we have to wait for new results of one of the most promising exoplanets. Kepler 452b is probably the Kepler telescope's most famous find. Unofficially nicknamed Earth 2.0, this planet orbits in the habitable zone around the star Kepler 452, very similar to our Sun in size, temperature, and brightness, 1,400 light-years away. Kepler 452b is probably 5 times the size of Earth and has a radius half the size of our planet. Therefore, it takes about 385 days for the exoplanet to completely bypass the star. The average surface temperature of the planet reaches 17 degrees Fahrenheit. The enormous distance between us and the exoplanet makes it impossible to know for sure if it's rocky. NASA researcher John Jenkins and researcher Jingjing Chen even believe it's unlikely to be Earth-like in composition and could be a mini Neptune. What's interesting is scientists even took several years to test whether Kepler 452b really exists. It was discovered in 2014 during a Kepler Science Operations Center test, although it had previously been undetected for 4 years due to equipment errors. Because of doubts about its existence, scientists rechecked the data for several years before finally confirming the planet in 2016. Nevertheless, the question of the habitability of Kepler 452b remains open. According to astronomer Douglas Caldwell, the planet has enough gravity to support water and a biosphere. Moreover, because of its long habitable zone, it may contain all the necessary chemical elements for the origin of life. Moreover, according to Jenkins, there may even be plants that can synthesize oxygen just as we do. However, there is one problem that may cast doubt on the development of life on an exoplanet: its star. Kepler 452 is older than our Sun, so it's about a bit brighter than our Sun. And in addition, Kepler 452b receives 10% more sunlight than Earth. Since the exoplanet is even larger than Earth, it could be exposed to high temperatures. This means that Kepler 452b could have a very strong greenhouse effect, causing all the water to boil off, making the surface hotter. Therefore, the distant exoplanet may already be a fading world rather than a thriving one. Kepler 452b cannot be accurately analyzed because of its gigantic distance, nor can we truly determine whether we could live there. Although, on the other hand, the discovery of an older planet with a similar star to ours will help us learn more about what may await us in the distant future. Another exoplanet recently discovered by Kepler 186f is one of the Kepler 186 planets orbiting in the habitable zone. The Kepler 186 planetary system is 580 light-years away and has 5 confirmed planets larger than our Earth. All of these exoplanets have a number, beginning with Kepler 186b and ending with an F. The system's exoplanets, with the exception of the F ones, are too close to their star, a cold red dwarf, so their habitability is probably unlikely. Kepler 186f is about 1.5 times larger than Earth and also has a larger radius, but its orbital period is only 130 days. In addition, because of its distance from the central star, the exoplanet can orbit around its axis without experiencing wave blocking and thus distribute temperature more evenly across its surface. Moreover, Kepler 186f probably receives a 32% lower stellar irradiation dose than Earth, but because the planet is in the habitable zone, even though its radiation energy is low, it can collect and store liquid water. But what is the composition of Kepler 186f? It's not yet possible to establish that. However, scientists suggest that for this planet, so far, there are 3 scenarios of how its composition may be: consisting entirely of water or ice, consisting entirely of iron, and having the same composition as Earth. That is, 1/3 of debris and 2/3 rock. Also, presumably, the atmosphere of the exoplanet is unlikely to contain much hydrogen. It could, moreover, have a helium-hydrogen cover, but the UV exposure of the star could have almost completely destroyed it. Nevertheless, the planet is still considered potentially habitable. According to the simulation team of scientists led by Emmeline Beaumont, organisms could develop on Kepler 186f if it is still rocky and has an atmosphere consisting of water vapor, nitrogen, and carbon dioxide. Interestingly, the researchers also believe that oxygen photosynthesis, though less productive, is possible on the planet if it is rocky. The last exoplanet on our list found by Kepler is Kepler 62f. This planet, like the previous one, is located in the habitable zone, Kepler 62 planetary system, 1,000 light-years away. The central star is generally similar to the Sun but differs in size and slightly in temperature. It's about 3 times smaller than our star, and its temperature is about 8,410 degrees Fahrenheit, and that's when the Sun's temperature would measure up at 9,940 degrees Fahrenheit. There's also 5 major planets orbiting the star, and 2 of those, Kepler 62f and Kepler 62e, are at the limit of habitability. Kepler 62f is a more likely candidate for the development of life than 62e because the latter is at the very edge of the zone. It's been suggested that it could probably be a mini Neptune and experience a strong greenhouse effect, almost completely ruling out life there. On the other hand, Kepler 62f is deep in the habitable zone. Therefore, it may not be blocked by tides, but it's also slightly heated by the star, receiving about as much light as Mars. Nevertheless, established data regarding its size, the exoplanet is 1.5 times the size of Earth, and its orbital period of 267 days may suggest the planet probably has water and a very promising candidate for habitable plants. Interestingly, according to research, Kepler 62f may even have the same seasons as ours, as hinted at by its axial tilt. Moreover, the exoplanet could hypothetically have a satellite to stabilize its tilt. The composition of Kepler 62f remains uncertain. However, as in the case of Kepler 186f, it's very likely that it could be rocky. Still, to support life, it needs to have an atmosphere 3 to 5 times denser than Earth. It must contain several times more carbon dioxide to remain warm and contain liquid water. Therefore, only further observations will answer whether Kepler-62f is inhabited. The next planet, already a little closer to us, 48 light-years away, is called Gliese 1214b. In the case of this planet, scientists are very confident that it may not be rocky at all, but completely watery. The exoplanet orbits a red dwarf and is currently the only planet detected in the system. Gliese 1214b is about 8 times more massive than Earth and has twice its radius. However, it's much smaller than ice giants like Neptune, so it's classified as a super-Earth. Also, the planet spins just 1.2 million miles from its star, making a complete revolution in 38 hours. So the temperature of the exoplanet's surface is very high, ranging from 248 degrees Fahrenheit to 539 degrees Fahrenheit. But then, could organisms like those on Earth exist on Gliese 1214b? Well, let's take a look at the data we now know. Gliese 1214b most likely consists almost entirely of water, including the core. However, it's still difficult to say for sure whether Gliese 1214b is an oceanic planet or a mini Neptune. Also, theoretically, 5% of the planet's mass is the atmosphere. The upper layers of the water planet are probably covered by clouds, so it's difficult for scientists to accurately determine the chemical composition of the planet and its atmosphere. However, according to the studies of the spectra of exoplanets, their atmosphere may be dominated by water vapor, which can be explained by the active evaporation of water or hydrogen. In addition, the atmosphere has recently been found to contain helium. Initially, the presence of this gas as a component of the primordial atmosphere was excluded. The presence of helium could not only tell scientists more about the evolution and development of such planets, but could also contribute to the formation of an atmosphere with high metallicity, that is, with the content of elements heavier than hydrogen and helium. On the other hand, researcher Leslie Rogers suggests that there are several scenarios of what Gliese 1214b could have originally been to get such a dense gas envelope. For example, it could have been entirely rocky with volcanic activity that filled the atmosphere, or a gas-ice stone planet with a metallic core, silicate mantle, layer of water ice, and gas that trapped helium and hydrogen during its early formation. Nevertheless, the planet's still full of mysteries for astronomers. Gliese 1214b is very promising in terms of habitability, so we'll wait for new information about it. The next interesting planetary system is Teegarden. The central star of this system is a red dwarf, nearly 10 times smaller than the Sun and half as cold, which makes the star Teegarden close to a brown dwarf. The star is 12 light-years away and has 2 confirmed planets orbiting it at a short distance. These 2 planets, TGS-C and B, both may be habitable. TGS-C and B are probably some of the closest sized planets to Earth. TGS-B is much closer to a dwarf. Its orbital period is only 5 days, while TGS-C is 11 days. Both planets are blocked by waves. Despite how cold the central star is, TGS-B has an equilibrium temperature of 82 degrees Fahrenheit, which is slightly higher than Earth's temperature of -1 degree Fahrenheit, but still fairly close. TGS-C, on the other hand, has an equilibrium temperature of -52 degrees Fahrenheit, which, although smaller, is still close enough to Earth. What's interesting, a group of researchers led by Dr. Matthias Zeichmeister suggests that TGS-B may be experiencing a strong greenhouse effect, which just raised its temperature. Nevertheless, given this and the similar amount of stellar fluxes received by Earth, both planets could support liquid water. TGS-C and B also probably have a similar earthy stone composition. It's also suggested they may have an entirely aqueous nature. Their atmospheres are unknown, however, it's thought that they may have weak magnetic fields, delaying the erosion of the atmosphere by stellar winds. Exoplanets may have had stronger fields earlier when the star may have still been active, but its strong flares and winds may have reduced the effectiveness of the fields. Nevertheless, scientists suggest that one of the TGS planets may be habitable. Comes to the atmosphere being heated like Earth, since the central star is still capable of reproducing a habitable atmospheric envelope. Next in line is planet Ross 128b. It's one of the closest planets to our solar system. Ross 128b and its star are only 11 light years away from Earth. The star Ross 128 is a red dwarf, one of the least active nearby stars, with a rotation period of 121 days. Recently in 2017, scientists discovered Ross 128b using the HARPS instrument. They were able to determine that the exoplanet's about 1.5 times the size of Earth and has an orbital period of 9 days. Therefore, it could probably be blocked by the tide. The exoplanet receives only 1.4 times as much energy from its star. Therefore, the temperature of Ross 128b can reach minus 76 to 80 degrees Fahrenheit. However, it's not yet possible to say for sure if the planet has water on it or if it's in the habitable zone, but the presence of water can be confirmed if the planet is found to have an atmosphere. On the other hand, researchers believe that the exoplanet is very likely rocky. Moreover, it may contain a mixture of rock and iron. Also, a team of scientists with lead author Diogo Suat found traces of various elements important to life on the star: carbon, oxygen, aluminum, calcium, potassium, etc. The researchers speculate that Ross 128b may have the same composition. Interestingly, Ross 128 may one day become the closest system to us, surpassing even the planetary system Proxima Centauri, which is about 4 light years away. The point is that Ross 128 is getting closer to us, so in 79,000 years it'll probably come very close to the solar system. Ross 128b has another interesting fact, this time related to alien life. Scientists at the SETI Institute studying signals from red dwarfs noticed strange repetitive signals with a frequency of 5 gigahertz coming from Ross 128. It didn't sound like interference, as there was no such signal from the other stars being studied at the time. However, listening to the star again later, scientists heard nothing. It turned out this unusual signal was probably coming from one of the geostationary satellites. Although we've not been able to detect alien life in the Ross 1280 system, its planet may be one of the most likely candidates for habitability. Hopefully, the next study of the exoplanet Ross 128b will be able to determine for sure if there's an atmosphere with water. Another exoplanet we want to tell you about is Wolf 1061c. This planet, together with its red dwarf star in the constellation Ophiuchus, orbits only 14 light years from Earth, making it the 5th closest system to us. The star, Wolf 1061, is very dim and not very active, with a rotation period of probably 89 days. However, it has an interesting feature. It has high proper motion, meaning it moves quite fast in outer space. In addition to Wolf 1061c, the planetary system has 2 more super-Earths, Wolf 1061b and Wolf 1061d. However, they cannot possibly be suitable for life. The central star is about 1.8 times cooler than the Sun, so Wolf 1061d is very cold because of the long distance and also could be a mini Neptune, while Wolf 1061b is very hot because of the powerful greenhouse effect, since it orbits at a distance of 3.5 million miles. Still, Wolf 1061c, being between the 2 planets but close to the inner edge of the habitable zone, could probably have good conditions for life. Wolf 1061c is more than 3 times the size of Earth. Moreover, its radius is also 1.6 times larger than our planet, although it has a short rotation period of 18 days, so it may have a density close to Earth's and could be a rocky exoplanet. However, because of its proximity to the star, Wolf 1061c may be blocked by tides. The planet also has a probable equilibrium temperature of -58 Fahrenheit, which is less than Earth's. but it may be enough to sustain water. Nevertheless, despite the rather optimistic predictions for Wolf 1061c's habitable, some scientists believe the exoplanet may have living conditions similar to those of Venus. For example, astronomy professor Stephen Kane believes the eccentricity of the planet often becomes completely circular, so the orbit may for some time be completed in the Venusian zone, which leads to the disappearance of water and a Venus-like atmosphere. Although, on the other hand, the professor also says that when the planet's orbit changes back to almost elliptical, it can cool down, which means, given the likely difficult conditions on Wolf 1061c, it could be habitable and retain water. About 100 light-years away is the large-scale planetary system TOI 700. Like many systems on the list, the central star is a red dwarf, about 1.7 times cooler and about as much smaller as the Sun. The star, TOI 700, is inactive with a probable rotation period of 54 days. 4 confirmed planets from TOI 700b to TOI 700e orbit around it. All of them could likely be blocked by tides. Also, all of the exoplanets are slightly larger than Earth, with the exception of TOI 700e, which almost reaches the size of Earth. The inner planets of TOI 700b and c are unlikely to be inhabited. TOI 700b is possibly rocky, but most likely red-hot. TOI 700c, on the other hand, may be sub-Neptune, so it may be too cold for life to develop there. TOI 700d and e are in turn in the habitability zone. By the way, TOI 700e rotates before TOI 700d because it was not detected in the first studies. Both planets are probably in the joint resonance 4-3 and are likely rocky and may contain water. Moreover, TOI 700d may contain even more fractions of the open ocean than other exoplanets on which life is possible, such as Proxima Centauri b. The radii of both exoplanets are several times smaller than Earth's 27e and 37 days, respectively. This may also hint at less powerful winds than on presumably some of the potentially habitable planets in the TRAPPIST-1 system. The question of atmospheres on the planets is still open. TOI 700b receives 35 times more stellar radiation than Earth, which probably could have damaged its atmosphere. However, scientists believe that the planet could still retain a dense atmosphere for billions of years, so TOI 700d could still have an Earth-like secondary atmosphere provided there is a magnetic field. Also, TOI 700d probably reflects a lot of sunlight, so it may be cooler. TOI 700e, because of its recent discovery, has not yet been investigated in detail. However, it may hypothetically have a Venusian climate. Like Wolf 1061c, this planet has almost zero eccentricity, although the circular orbit may also mean the planet can maintain a stable climate and moderate surface conditions. It may also be able to change the elongation of its orbit like Wolf 1061c and therefore cool down while retaining water, but that remains to be seen. Still, for the moment, TOI 700e remains presumably inhabited, and only further observations will be able to give an exact answer. The last planet we'll tell you about is Gliese 273b or Luton b. It's located very close to us on the cosmic scale, 12 light-years from Earth. Luton b is very similar to Earth in many characteristics. Thus, the exoplanet is 2 times larger than Earth and has an equilibrium temperature of 7 degrees Fahrenheit, which is very similar to the temperature of our planet. It also, along with a second discovered planet, Gliese 273c, orbits the red dwarf star, 4 times smaller than the Sun, with a rotation period of 118 days, which makes it not very active. The exoplanet itself makes a complete revolution in 18 days. With such proximity to the star, planets tend to be blocked by tides. However, in the case of Luton B, there is one peculiarity. Most likely, it may additionally be in resonance. That is, Luton B may rotate, alternating sides instead of heating only one. Given the temperature and the fact that the exoplanet is in a habitable zone, we can assume there's water there. Studies suggest that the planet may be a water world. Moreover, the exoplanet probably still experiences wave heating, meaning that it receives energy through resonance, which may also suggest the presence of water and the possibility of a biosphere. The composition of Luton B has not been precisely established. It's believed that it may be either completely rocky or composed of 50-50 ice and rock. It's also not yet known whether the planet has an atmosphere, and only further research will help us find out for sure. Finally, there's another interesting fact about this system. In 2017, the METI group, a separate part of SETI responsible for the search of extraterrestrial life, sent a radio message to the Luton star and its planets. The radio signal contained a musical greeting and information on how to decode the signal. It'll take 12.5 years for the message to reach the potentially inhabited planets, so it will be a long time before we get a likely response. There are a great many planets in the universe. Our scientists continue to tirelessly search for and study Earth-like exoplanets on which we can live in the future. Still, no matter how vast the cosmos is, we hope that one day we'll find Earth 2.0. Perhaps it'll be different from our planet in some way, and we'll not be able to observe there, for example, the same plants or even a similar day and night cycle. Therefore, humanity will probably have to say goodbye to Earth one day and go to another solar system, to a new planet, for new life. The solar system is unique because of its special structure and, most importantly, optimal conditions for life to develop. Therefore, missions that are aimed at finding planets we could potentially inhabit and trying to find them in similar star systems. But what if we tell you there is a planetary system not far from us that is very similar to ours? And more to that, it consists largely of planets that are similar to Earth. Today we'll tell you about the TRAPPIST-1 system and whether or not its planets would be able to support life. The TRAPPIST-1 system was discovered very recently. In 2016, a team of scientists led by Michael Guillaume and Susan Lederer discovered 3 planets orbiting an ultra-cool dwarf star known as TRAPPIST-1a, 40 light-years, 235 trillion miles, 378 trillion kilometers from Earth. However, the very next year, NASA astronomers made a new discovery using the Spitzer Space Telescope. Turned out there are as many as 7 planets in this planetary system. However, TRAPPIST-1 has no gas giants like Saturn or Jupiter. Almost all of its planets are structurally similar to Earth. These findings led scientists to speculate that perhaps TRAPPIST-1 may have the potential for life to exist there. So what does the TRAPPIST-1 system look like? The central star, as we've already mentioned, is a red dwarf. It has 7 planets revolving around it, roughly the size of Earth. All of them have the name TRAPPIST-1, but each planet has an individually assigned alphabetical index from TRAPPIST-1b to H. Unlike our solar system, TRAPPIST-1 has several other important distinguishing features. First, all the planets in this system only face the parent star with one side, the same way as we see the Moon. The time it takes the planets to rotate around their axis is the same amount of time it takes them to orbit the star, which means that one day on these planets is equal to 1 year in length. This process is called tidal locking. It's caused by the gravitational interaction between space objects. Secondly, all the planets are very close to each other. It is likely that the desensification of the system is caused by an internal migration of the planets, which also led to their resonance. For example, the distance between the star and its nearest planet, TRAPPIST-1b, is only 11 million miles. For reference, the average distance between the Sun and Mercury is 36 million miles. This means that these planets might be heated better due to relative proximity to their star as well as interplanetary gravity, which would allow them to retain water inside themselves. Does this figure that all these planets can hypothetically be habitable? Let's try to figure this out. First, let's take a closer look at the central star. TRAPPIST-1a is very cold and small when compared to our Sun, for example. Its surface temperature is only about 4,154 degrees Fahrenheit, whereas the temperature of the Sun is close to 9,930 degrees Fahrenheit. Its size can be compared with Jupiter and its mass approximately 13 times smaller than the Sun's mass. However, red dwarfs burn their hydrogen supply much more slowly, which means they can exist for a very long time, several trillion years, in contrast to the age of stars like the Sun, which is closer to 10 billion. According to research by Adam Bergesser of the University of California, TRAPPIST-1a may be about 7.5 billion years old, which would be considered a relatively young age for such stars. However, if red dwarfs are so cold, how could they heat the entire planetary systems? True, for a long time there was an assumption that red dwarfs were not capable of supporting life, but the discovery of TRAPPIST-1 has changed scientists' view. The peculiarity of the proximity between the planets and the temperature of the star maintain, on average, moderate temperatures in the range from -171 degrees Fahrenheit to 258 degrees Fahrenheit on these planets. Now, what's more, thanks to relatively low temperatures as far as stars go, dwarfs can help conserve water on the planet in their planetary system, even the ones closest to it, and also, interestingly, funnel amino acids and important chemicals through their flares. On the other hand, dwarfs can expose nearby planets to strong UV radiation, creating conditions unsuitable for life. Therefore, let's move on to the planets themselves now and find out how the characteristics of their system affect them and the potential life on them. The first on the list is TRAPPIST-1b. Its radius is 10 times larger than the radius of Earth. Similar to Earth, it's also made of rock, iron, and likely ice. Interestingly, 1b may even contain a small layer of water, about 0.2% of its total mass. Although some scientists are inclined to believe that the planet is completely dry and has only oceans of magma. However, the conditions on this planet are far from earthly. Obviously, the proximity to the parent star must result in a very heated surface. Moreover, the gravitational influence from the star may cause strong volcanic activity, heating the surface even more and melting the internal rocks. However, the temperature on 1b is too high even for this. Temperature there reaches 2,156 degrees Fahrenheit, which is 2.5 times higher than on Venus at 860 degrees Fahrenheit. The reason for such temperatures may be the high density and possibly atmosphere in which gas accumulates after volcanic eruptions, which prevents heat from leaving the planet. The next planet, TRAPPIST-1c, is similar in composition to TRAPPIST-1b, but most likely has neither ice nor water. It is the heaviest planet in the entire system, even though it has a smaller radius than 1b. It's also very likely that it has high levels of geological activity. That's due to the influence of the star and orbital resonance. The exact surface temperature of 1c, it's unknown. The star can heat it up to about 158 degrees Fahrenheit, but the internal activity of the planet is capable of raising the temperature several hundred degrees. However, it will most likely not reach the same temperatures as 1b due to the atmosphere, which is likely less dense. One of the features of 1c is its massive core made of metal, which is almost 1.5 times larger than Earth's. Because of this, its large magnetic field is able to protect the planet from stellar wind, a stream of charged particles that could destroy the atmosphere. However, 1c is unlikely to contain water, and like 1b, the surface heats up significantly due to gases, which makes life on these planets impossible. Next, we have TRAPPIST-1d, one of the smallest planets in the system, with a mass about 3 times smaller than Earth. It's composed of rock and metal, but very likely, like 1b, it must have an ocean, a layer of ice, or a dense atmosphere. And that's according to the theoretical research of its mass and radius. Astronomer Vera Dobos believes that the surface on 1d could be as reflective as the surface of Earth. This means that 1d may have liquid water and a dense atmosphere, which in turn may even contain ozone, which would protect the planet against harmful radiation. Moreover, the scientist also suggests that unlike 1b and 1c, 1d can avoid a mass-scale greenhouse effect, which would greatly increase surface temperatures due to its small mass. However, despite strong evidence, some scientists have other assumptions about the possibility of life on TRAPPIST-1d. Researchers from the University of Washington believe that 1d receives more energy from the star than the more distant planets, and therefore it may be similar to our Venus with a pronounced greenhouse effect like on 1b or 1c. Therefore, life is unlikely to develop there. On the other hand, it may also have some hydrogen in the atmosphere, which would prevent it from overheating. Furthermore, its atmosphere may contain a very little CO2, which would have a negative effect on the emergence of life. In addition, its orbit is almost circular, as in 1d may be heated slightly due to gravity. Finally, due to its small size, the planet may not have a magnetic field. Therefore, the stellar wind could carry away volatile particles from the atmosphere, including water, as it may have happened with Mars. The conditions on 1d are quite controversial, so it requires further research from scientists. But the fourth planet in the TRAPPIST-1 system presents the greatest interest to the scientific world. TRAPPIST-1e is more similar to Earth than other planets in the terms of radius, density, and heat received from the central star. Its orbit is 2.7 million miles away from the star, which results in the planet completing a full revolution in 6 days. Its composition as a whole is very similar to that of 1c. 1e is mainly composed of rock and metal. Does that mean there's no water there, like on 1c? NASA researchers believe that 1e is in a so-called habitable zone, a distance within a planetary system where it's neither too warm nor too cold, which also keeps water in its liquid form. Therefore, it's very likely that 1e may contain water, and in quite large quantities, in fact. Researcher Vera Dobos suggests that an excessive greenhouse effect may not be characteristic for this planet, unlike all the previous planets we've discussed so far. This means that 1e would be able to maintain a moderate temperature, maintaining entire oceans on its surface. Moreover, due to its weight, 1e may have an atmosphere that's not too dense. A group of scientists led by astrophysicist Martin Turbet believes that the atmosphere on 1e may be rich in CO2 and contain almost no hydrogen, preventing the planet from overheating. Additionally, 1e can retain its atmosphere for an extended time despite the impact of the stellar wind, and may therefore create optimal conditions for life. However, the exact mass of 1e has not yet been established. Therefore, just as with 1d, it's difficult to say for sure whether or not there may be water on it. Although scientists largely agree on the presence of an ocean and the planet's potential habitability, some suggest that it may be a homogeneous rocky planet. The following planets, TRAPPIST-1f and 1g, are also presumed to be generally similar in their mass, rocky structure, radius, and density to planet 1e. However, that's where the similarities end. Both planets are at a great distance from the star, one 3.6 million miles away, and the other is 4.3 million miles from the parent star, respectively, also within the habitable zone. However, their surface is not as heated by the red dwarf, and scientists suggest that both of them may be covered with a solid layer of ice. Nonetheless, they may have the same heating potential as 1d from gravitational interaction with the star. That is, despite the very little heat from the star itself, planets can be heated properly from the inside, and therefore they are likely to have a global ocean under the ice. Furthermore, likely due to their high internal temperature, the water on these planets could evaporate, forming a dense atmosphere rich in oxygen. And so it is possible that their surface may not be that cold, but could even be warmer than Earth's. However, according to research by a group of scientists led by Bill Quarles, up to 20% of 1F is made of water. Given its possible internal heating as well as the mass of the planet, likely smaller than that of Earth, scientists believe that water can only exist there in the form of clouds. Equally, 1G also evolved with a lot of water. According to some scientific reports, the depth of its ocean can be 416 miles. Although such ample amounts of water may seem beneficial to life, oceanic evaporation can significantly increase the oxygen pressure in the atmosphere, casting doubt on the possibility of any development of a living organism. Therefore, despite the likely presence of water, the question of the habitability of these planets requires new research focused on their atmosphere. And finally, the seventh planet, TRAPPIST-1H, is the most removed from the star as well as the smallest in the entire system. Unlike all the other planets, 1H may be composed almost entirely of water and is likely to have very little rock in its composition. However, it's likely also that 1H is heated much less than the others. The parent star alone would bring the surface temperature to only about negative 153 degrees Fahrenheit. Furthermore, some scientists suggest that the amount of heat generated by gravity would also be quite low for 1H. However, researcher Kathleen Mant believes that 1H may have a lot of volcanic activity, spewing water instead of lava. That would mean the planet's able to replenish its atmosphere due to the emitted gases. Additionally, the remoteness of 1H allows it to firmly retain its atmosphere, probably consisting of nitrogen and methane like on Titan, since the stellar wind hardly touches it. And yet even this quality does not speak in favor of life on the planet. It's still very cold and therefore probably cannot sustain water in liquid form. But the question remains, could life hypothetically exist in this TRAPPIST-1 system? The tidal lock is not great for sustaining life because one side of the planet's always scorchingly hot and the other side is freezing cold. However, almost all planets in the system can cope with this drastic difference in temperature due to their water content and their atmosphere. The heated ocean and atmosphere can transfer heat to the colder zones, maintaining the temperature balance. Nonetheless, only the middle planets, 1D and 1E, meet the criteria to be on the list of potentially habitable planets. 1B and 1C are too hot, may have lost water due to their gravitational relationship with the star, whereas 1F and 1G and 1H are probably not warm enough due to the weak greenhouse effect, or they're also quite hot. However, 1D and 1E still require extensive research since conditions on these planets may turn out to be more similar to Venus, although 1E is very unlikely to fall into that category. In fact, if both planets were covered in ice, they might still be habitable. The TRAPPIST-1 system remains very interesting to all of us. In 2021, NASA sent the James Webb Telescope to the L2 Lagrange point with a view to study TRAPPIST-1 among other things. Therefore, we can expect new data on a distant system very soon, which would reveal more secrets about the origin of our universe and possibly even the origin of life.